So I'm going to talk about some scattering techniques and geometries, especially specific to some of the SSRL beamlines. So this will be a little bit of an overview of sort of general techniques and geometries, and then some specifics for SSRL beamlines. So the main motivation, X-rays are an excellent tool for studying the properties of a material. Now this can mean a lot of different things. This definitely includes the intrinsic properties of a material, the crystalline structure, for example. But oftentimes those intrinsic properties are not sufficient to really describe the things that you care about, because you may care about sort of extrinsic properties like the texture of a material, the micro or the nanoscale morphology, and then of course the properties that you're interested in may change depending on exactly what you're doing to the sample. So as a function of temperature, as a function of atmosphere, as a function of voltage, any number of things. And so really what you have to do is design the experiment to the sample. And so the goal of this is really not to give you a list of the best ways to do anything in particular, but really to encourage careful thought regarding your experimental design. So every experiment should be a little bit different. The idea is to make sure that you've thought carefully about what is going to give you the best possible result. So I'm going to go over very briefly the basic scattering experiment. This will look a lot like some of Lenson's stuff, but I'm not going to go into too much detail. Then I'm going to talk a little bit about small angle scattering, reflectivity, powder diffraction, and thin film diffraction. And so the basic scattering experiment, you have some scattering object. This is your sample. You bring X-rays and shine them onto the sample, and then they scatter. And this is really what all of the scattering experiments that you can do at SSRL come down to. And really all we want to know is what is the intensity of that scattered radiation in any given direction. And then you can say, if I move my sample, if I reorient it, how does that scattering change as I reorient my sample? And so the thing that we're going to talk about is we're going to deal in Q. And so Lenson explained this, so I'm just going to go through it very briefly. It's basically the momentum transfer. So the X-rays have some wave vector. They carry momentum. It's elastic scattering, and so the magnitude of the momentum does not change, but the direction does. And so the momentum transfer is really just defined as the difference between these two wave vectors. And you can work through the math, but basically what you come out with is that Q is 4 pi sine theta. Theta is the angle, actually it's half of the angle into which you scatter, over the X-ray wavelength lambda. And all that we actually care about is the intensity as a function of Q. So Q is the natural unit to work in for a scattering experiment. I should also note Q is a vector. So it has more than just a magnitude, it has direction. For a lot of experiments, we sort of ignore the direction. We talk about just the magnitude. But the fact that it does have a direction can be very important for certain samples. And so keep that in mind, even though we'll sort of simplify as we go through some of the discussion. So the first thing that you want to do in designing an experiment is choose the appropriate length scale. And so Q is inversely proportional to the length scale that you probe. And so at very high Q, you're probing, at very low Q, you're probing very big things. And so this would be something like USAC, which is ultra scattering. It's sort of the intermediate, at least for these purposes, is small angle X-ray scattering, so not quite as small of an angle, so that means slightly higher Q. And then what we're going to call wide angle X-ray scattering, which is going to encompass a huge number of things, diffraction primarily. The terminology is somewhat fluid. But the first thing that you want to do is ask, what length scale do I care about my sample? Do I care about what's happening on the micro or the nanoscale, or do I really care about sort of the atomic level details? Because that will determine what range you want to look at and what technique you want to focus on. The other thing that you want to worry about is the appropriate sample geometry, and this depends a lot on what form your sample takes. And so if you think about crystallography, if you have a single crystal in reciprocal space and scattering, you're going to have these very discrete points. And so you need to worry very much about how your crystal is oriented so that you can make sure that you are actually measuring one of these points that you care about. If you have something that's made up of a large number of these single crystals that are more or less oriented with each other, you're going to end up with sort of streaks. And again, you need to worry about how your sample is aligned to make sure that you're actually lighting up the thing that you care about. You can go to the other extreme and have a huge number of crystals in all sorts of random orientations, and that's what we're going to call a powder, and then you get these continuous rings in scattering space. And in this case, you really don't care about how your sample is oriented, because if you look at all of the crystals in your powder, they have a random orientation, and so any orientation of the bulk sample is equivalent to any other. And so you really don't care so much about the sample orientation in that case. And so just a very quick recap then, small angle X-ray scattering, you're looking at very low Q regions, which means you're looking at very large things. And by large, what I mean is length scales of sort of 1 to 100 nanometers. You can do reflectivity, which can probe things on a very small scale. But what you're doing there is really looking at layered structures. And so this is a directional measurement. You're looking at just the depth resolved structure. And you can really resolve things anywhere from the scale of angstroms up to nanometers. And then powder diffraction or wide angle scattering, you're really looking at atomic length scales. You're probing to very large Q. And so you're looking at very small things on the order of angstroms. And then I guess also sort of in that is thin film diffraction, which can be polycrystalline, which is more or less a powder just in thin film form, which works the same way. Or epitaxial, where you're really looking at sort of a single crystal film on top of a substrate, where again you're looking at atomic length scales, including the surface and interfacial structures at an atomic level. And again, as I said, the terminology for all of this can be somewhat fluid. Whether or not you call something diffraction or wide angle scattering depends a little bit on who you're talking to. They're more or less interchangeable though. So to translate this into some of the SSRL beamlines, we really have 5 scattering beamlines at SSRL. And so we have beamline 1.5, which is meant for small angle scattering. And so you can measure things like thin films, you can do solution phase measurements, you can measure things in transmission, and you can do this quickly, which means that you can do real-time measurements. So you can do in situ, you can watch something as it's changing. We have beamline 2.1, which is more or less a powder diffractometer. So this is what we're going to call a 2-circle diffractometer. I'll talk a little bit more about that in a minute. So this is great for powder diffraction or reflectivity primarily. You can do very good quality reflectivity measurements there or high quality powder diffraction. Beamlines 7.2 and 10.2 I'm going to more or less lump together. They have very similar capabilities. If you're interested in the differences, we can talk about that. I'm not going to go into too much detail here. But these are very general instruments where you can do things like single crystals because you have a lot of degrees of freedom in how you orient both the sample and the detector. And so they're very good for single crystals, surface diffraction if you want to look at surfaces, and they can also reproduce the capabilities of beamline 2.1, although it's a little bit overkill for a lot of things. And then we have beamline 11.3, which is really meant to do thin film or transmission powder diffraction in sort of a rapid mode. So this is equipped with a large area detector, so you can collect a lot of scattering in a very short amount of time. And so again, this is really good for real-time experiments. If you want to watch something as it's evolving, as you do something to it, this is a great place to do that. So we have different detectors, and Tim is going to talk a little bit more about this in a later talk. But basically, we now have area detectors available on all of the beamlines. The diffractometers 2.1, 7.2, and 10.2 can also be equipped with point detectors, so you're only measuring one spot at a time. This means that it can be quite slow, but there can be definite benefits to doing a measurement in that geometry, and I'll talk about that a little bit more. And then, of course, you have just some various advantages and disadvantages. I'm not going to go into it too much. Some of the ones that I will briefly mention on 1.5, you're typically looking at a very small Q range because it's meant for small angle scattering. And then on beamline 11.3, you have no control over your X-ray wavelength. That instrument is at a fixed wavelength, so you can't vary the wavelength. The other beamlines, you can tune the wavelength to an appropriate X-ray energy as the experiment needs it. And we can talk more about what that means by the experiment needing a certain energy. So I'm going to just do a brief outline of the different beamlines. This is beamline 1.5. So this is a photo of it down here, and this is a very general schematic of what's going on at the top. So the X-rays are coming out of this little port in the wall here. The sample in this case would sit sort of here. And so the X-rays come in, scatter off of the sample, and then way down here, sort of behind this black strut, is a detector, a large area detector. And then in this box is a beam stop, which basically means that the direct beam that comes through gets stopped before it hits the detector because it's very, very bright, because as Lenson said, scattering is a very inefficient process, and so if you look at the scattered signal relative to the direct beam signal is many orders of magnitude bigger. The detector typically doesn't like that. You don't want to damage the detector, and so you put a beam stop in place. And so the energy range you can tune between about 4 and 20 keV. The low Q limit is about 0.0009 inverse angstroms, which corresponds to sizes of about 130 nanometers. Beamline 11.3, I'm going to go out of order because this is a very similar setup. In this case, it's sort of backwards, so the beam is coming from this direction and moving here. Your sample would sit here, and this is your large area detector. I'm showing my schematic flipped just for convenience. So again, the X-ray comes in, hits your sample. In this case, the beam stop is right behind the sample, and then you have your detector. So one consequence of having the beam stop closer to your sample, it cuts down on background because the beam does not go through a lot of air that may scatter. But it also cuts down the very lowest angles because, as you can imagine, if you have something very close to your origin, the opening angle that blocks becomes a little bit bigger. And so you lose the really low Q information here, but it's mainly a wide angle scattering instrument, and so that's fine. And in this case, we can move the detector back and forth anywhere from about 150 millimeters to 400 millimeters, and that's a pretty good range for covering a lot of Q space. So then for the diffractometer beamlines, 2.1, 7.2, and 10.2, what I mean by a diffractometer is basically just a set of rotation stages with a common center of rotation. And so this is a lab powder diffractometer. This is one of the Brooker instruments. This is your X-ray source. This is your detector. Your sample would sit here. And then both this arm that the source sits on and this arm that the detector sits on can move in angle around the same center of rotation here. For synchrotrons, we do not have the synchrotron on a movable arm, so that can't move, but we can move the sample instead. And so this is basically a very rough schematic of what beamline 2.1 looks like. In the center, you have a rotation stage that your sample sits on, and then a little bit further out, on the same axis of rotation, you have a stage that your detector sits on and can move around. And so these diffractometers are typically referred to by the number of circles. So 2.1 is a 2-circle because I have 2 rotation stages. 10.2 is a 4-circle because there are 4 different rotations. And then 7.2 is actually a 6-circle. We have a lot of degrees of freedom on 7.2. It's a little bit tricky to get good pictures that kind of show anything of diffractometers, but we've tried. So this is 2.1. This is where the sample sits. This is the sample rotation stage. This bigger thing here is the detector rotation stage. On 7.2 and 10.2, the sample sits inside of this circle, and then it can move along inside of this circle, and so that's one of the rotations. That circle itself can tilt. That's another one. The thing that it's on inside can rotate another way, and then you have the arm of the detector as well. On 7.2, the 2 additional circles are that the whole thing can rotate sort of around a vertical axis, both the sample and the detector. can rotate around a vertical axis, which you cannot do on 10.2. But the point of this is these diffractometers give you a large number of degrees of freedom to orient the sample and the detector so that you can look at the appropriate place in reciprocal space where the interesting information lies. And all of these can be configured with either a point detector or small area detectors. And typically our in situ chambers that, again, Doug will talk more about later, are more or less compatible with all of these. And so you can go from one to the other with the same setup if you need to as the experiment demands. So some practical considerations. I'm going to talk about the diffractometer setups and what kind of detector you want, and Tim will cover this a little bit more, but I want to give a brief outline. If you're using a small area detector, this comes with some pros and cons, as all things do. So you're looking at a reduced angular resolution, so you can't really resolve in angle very small features, but you do tend to get a very strong signal because you're looking at a fast and parallel detection. So one of these things typically has 100,000 pixels, which is the equivalent of 100,000 point detectors arrayed in a very small region. So you get a lot of signal very quickly. Now, every image is going to cover some small region of angular space, and so if you want to get full coverage, you have to stitch those together. That can come with problems. And you also have really no way of discriminating against background or fluorescence, and so the background on these measurements can be quite high. You can do another setup using a point detector, which is sort of a low-resolution solar slits. Basically, all this is a lot of metal plates arrayed parallel to each other so that you can only get light through in a very certain direction. If you're a little bit off axis, you'll hit one of the plates and you can't see through. This has, again, a reduced angular resolution. It's about the same as what you get from the Pilatus, about 0.01 degrees in 2 theta. You still get quite strong signal into the detector, but of course you're only using a point detector behind that, so you only get sort of one point at a time. And again, you really don't have a great way of discriminating the background, although you can use an energy discriminating detector to get rid of fluorescence. So you can have a detector that actually tells you what energy the X-rays it's detected are at. And so you can discriminate between the elastic and the fluorescence, which will have different energies. And that would be the vortex detector that you can put behind this, or you can use a photomultiplier tube. The highest possible resolution is to use an analyzer crystal. So this is actually the diffracted beam, or the scattered beam, would actually hit a single crystal of silicon in our case, and then diffract from that single crystal into the detector. And so this gives you very, very high angular resolution, but it also gives you very reduced signal, because now you're looking at the scattered signal from your sample, again scattering from something, and scattering is an inefficient process, and so you lose a lot of signal when you do this. You gain, however, because you can also cut down the background very significantly. And so even though you're losing signal, your signal to background can actually be improved using this setup. And this would just have a photomultiplier tube as the detector. So another important consideration is what your detector is actually measuring. And so if you have a small area detector, really what you're measuring is position. You're not measuring the angle into which something is scattered, you're simply measuring a position, and then you try to map that position into angle. If you're using solar slits or an analyzer crystal, you're actually measuring angle. You're measuring the true angle at which something is scattered into your detector, not simply position. And it seems like a subtle difference, but it's actually quite important. So again, some practical considerations about data collection. We can think about sort of the amount of time it takes to collect a diffraction pattern and the step size, the number of points that you need to collect. And so if we make a basic assumption that we want to cover a 2 theta range of about 5 to 65 degrees, so a total of 60 degrees of coverage, and we say that we want to count at 1 second every point, we can do some back of the envelope calculations, and if we're using a Pilatus, we may be able to cover that 60 degrees in only about 4 images. I'm sorry, in steps of 4 degrees. Have that wrong. So 4-degree steps will give us enough coverage to stitch all of that together. And so we're really looking at about 15 seconds of total count time. So this is a pretty fast measurement. If we need to use a point detector, then we have to take fairly small steps. And so if we take a step size of 0.01 degrees, we're looking at about 1 hour and 40 minutes to cover that 60 degrees. If our peaks are very sharp, so we're using an analyzer crystal and the sample is a very highly crystalline material, you may have to take quite small steps of 0.005 or 0.002 degrees. And now you're looking at anywhere from sort of 3 to 8 hours of data collection, which can be a little bit problematic, especially when you're looking at a certain amount of beam time and a certain amount of samples that you'd like to get through. So this kind of begs the question, why not just always use a small area detector to do this kind of measurement? And again, this comes back to some of the cons of using an area detector, one of which is that you're measuring position and not angle. And what this means is that you're very subject to alignment errors. And also you have no energy discrimination, and so you might see a very high fluorescent background. And for some samples, especially a flat plate sample or a thin film sample, it's difficult to do this with a constant measurement geometry. So what you end up with is sort of step-like changes in both the resolution and the background as you move the detector. And you do end up with somewhat limited resolution, and so you might end up with more peak overlap at the high angles. So in powder diffraction, the density of peaks grows as you move to higher and higher angle, and you start to get peaks that overlap quite significantly. And so if you have poor resolution, that problem gets exacerbated. So I want to go through what some of these issues are, and again, this is not to deter you from using something like a Pilatus. This is more to make sure that you're aware of the issues, and so that you can think through them carefully before coming and doing an experiment. And so what I have here, this is the sample. The incident beam is coming in. This would be the area detector, the face of it, and so the scattered X-rays can hit that, and we can detect where they hit on the detector. And then this is on a diffractometer arm, and so we can move the detector along this arc. And so ideally, every pixel of the detector corresponds to a scattered X-ray from a given angle from the sample position. However, area detectors, they see everything. And so scattering from anywhere that gets into the detector, you will measure. And so if you scatter from something that's back here behind the sample, that may just be air, that may be some piece of metal that's attached to the diffractometer, it may be anything. If it scatters from there and it gets into the detector, and it hits the detector here, the detector measures that, and you don't know if that scattered intensity came from here or if it came from your sample. Another problem is you may have misaligned your sample, which means that the sample is not sitting on the center of rotation of the diffractometer. It's displaced a little bit either back from that or a little bit below where the beam is. And this translates into a big problem, which is that you measure an intensity feature at the wrong position. And so if you think about where the scattering should happen, in this sort of faint outline here is where the sample should be if it's well aligned, and so this is what scattering you should see. If my sample is a little bit too low, below the beam, that means that I'm actually going to hit a little bit further along the beam path. I'll scatter that same feature into the same angle, but now I hit on the detector at a different place, and so I think that that feature is at the wrong angle. It's actually a little bit worse because that offset is not constant in angle. So if you're actually at a shallower angle, the offset may be a little bit smaller than if you're at a large scattering angle. And so it's not simply that everything gets shifted by a different amount depending on where you are. So there are different ways to measure a thin film. Basically, you can decide what angle you want to measure it at. And so there are sort of two that I'm going to talk about. One is what I'll call a symmetric geometry. You may be familiar with it as a Bragg-Brentano geometry, although that's somewhat specific to a lab source, and so it's slightly different, but still referred to that way at times. or a specular geometry as well. And basically all this means is that the incident beam and the diffracted beam make the same angle with respect to the sample. So this is also that in the parlance of the diffractometer, theta is at half of 2 theta. This is ideal for really thick samples. If your sample is effectively infinitely thick, this is great because it turns out if you work through the math, the illuminated volume from this geometry is constant as a function of angle. That's great because it means you don't have to do any correction for how much sample you're looking at any given point. Of course, if you have an area detector, you're measuring multiple angles at once, you cannot satisfy this for all angles at a time, right? You have to pick probably the center of your detector you can satisfy this for, but as you move out to the edges of your detector, you're no longer satisfying this symmetric condition. So the other way that you can do this is you can work at sort of a fixed incidence angle, an asymmetric geometry where the incident angle and the diffracted angle are not the same. This is also what you would probably call grazing incidence geometry because typically the incidence angle is fairly small. This is great for really thin samples, but it does come with a number of corrections that you have to think about, mainly that the diffracted intensity, in this case, is not a constant. And so you have to scale your intensities according to this. And if you look at what that looks like as a function of the incidence angle, so if you have an incidence angle of 2 degrees, this is the intensity correction. If you're at something fairly extreme like 20 degrees, you actually can't measure below your incidence angle. The sample will shadow the scattered intensity, but the correction can become quite dramatic if you're at fairly large angle. And so you need to worry about things like this if you're trying to do very accurate measurements. But there are advantages, certainly, to working at grazing incidence, namely that you can illuminate more of your sample. So if you have an incident beam, it has some height. Our beams are not infinitely small. And what that means is that at some angle for the sample, you get a footprint. And if this angle for the sample is lower, the footprint gets bigger, which means that you're seeing more material. It also means that you can get limited penetration into the sample. And so if your sample is a thin film on top of some substrate that you don't care about, this can limit the amount of scattering from that substrate, can cut down the background. And you can actually, if you're very careful and work at very, very low angles, isolate the scattering from just the film or even just the very surface of your film, if you're working very close to what's called the critical angle of your film. So the footprint correction, however, is something that you need to think about. This is especially true at somewhere like beamline 11.3. If you have a large beam footprint, because you're working at very low angle, that footprint actually gets projected onto the detector. And so what this can give you is very, very broad peaks, because if you have a big footprint, you're projecting that onto your detector, your peak suddenly looks like a square function, and it can be quite broad. And this is not what you typically want, because that's not what a good diffraction peak or good scattering peak should look like. And again, this is somewhat dependent on the scattering angle as well. This will not be a constant width or a constant peak shape correction as a function of 2 theta. Another problem, and this is actual data that I took to illustrate this. This is sort of a worst case scenario, but it demonstrates the point. This is a plate of Lab 6. So this is a standard reference material that is at most of the beamlines that you should measure to characterize the instrument. And this is using the Pilatus on beamline 10.2, and it's 2 images where I've just moved the Pilatus by, it looks like about 3 degrees. And so if I integrate the first image, I get this blue curve, and here's my Lab 6 peak. This is all some background. And then if I move the Pilatus to a different position, the peak shows up in the same spot. That's good. I've done a reasonably good alignment. But you can see my background is significantly different. And if I integrate both of these together and stitch them into a single pattern, you get these very funny little jumps in the background. And if you want to then go and fit your diffraction pattern, those are going to be very problematic. it's tricky to build a functional form for a background that's going to have some of these sudden jumps in it. And also, if your peak happens to lie right on top of that, that's going to give you a very funny peak shape that you don't really want to mess with. One way around this is to work in a more cylindrically symmetrical geometry. So you can load your sample into a capillary. And so in the cross section, this is your sample, beam comes in, scatters out, and it's basically the same no matter what angle you scatter into because it's cylindrically symmetric. And so this is Pilatus data on a sample in a capillary. There's no beam stop in place, and so you see I have this huge background from all of the air that the beam goes through. So this is all air scatter, because basically anywhere along the beam path, if the air scatters and it gets into the detector, I measure it. So if you actually use a crystal analyzer, you can basically get rid of almost all of that air scatter. And so this black curve is the same sample measured using an analyzer crystal, a high resolution measurement. And you can see I've sort of arbitrarily scaled it just to put them on the same thing. The number of counts in the high resolution data is significantly lower, and you can see that it's quite noisy. But the signal to background and the signal to noise is actually much improved. This is actually better data than what you see in the blue curve. And if you look quite closely, you see the impact of the improved resolution. In the Pilatus, I might think this is a single peak. In the high resolution data, I can very clearly resolve that that's actually two peaks close together. So again, the analyzer crystal, you're measuring angle, so you're not subject to these misalignment errors. Because you're doing Bragg diffraction off of a crystal to get into the detector, it eliminates anything that's not of the right energy, so you can get rid of fluorescence this way. Gives you very high resolution, but it is a point detector, and you need to take very small steps, and so getting good data can take a very long time. I'm going to shorten this section a little bit and just walk through the main benefits of the analyzer crystal. So this would be the crystal analyzer. It would scatter off here into a detector. And basically, the only thing that will scatter into the detector has to satisfy the Bragg condition, which means that it has to be the correct lambda, the correct energy, at the correct angle, and I set the angle just by how I align my crystal. The D spacing is set by what my crystal is, silicon 111, and so only things that hit at the correct angle of the correct wavelength will actually be detected. And so this is the main benefit to an analyzer crystal. I'm not going to talk about the misalignment issue so much, and I'm not going to talk about what determines the resolution in the interest of time, but we can talk about that a little bit later and how to maximize that resolution if that's what you really think you need. So basically for powder diffraction, the idea is think carefully about the experiment and make sure that you have a setup that really makes sense for what you're trying to do. Data taken with an analyzer crystal is really the gold standard. You're not going to get higher quality data than that, but it's often too slow or simply unnecessary for a lot of experiments. And so just because that may be the best doesn't mean it's what you should be doing. And then the sample geometry that you pick can have a large impact on the quality of the data when using an area detector especially. And so think carefully about that. Don't just use a Pilatus because it's fast and you can get through a lot of samples if you're going to have issues with what that data looks like because of the sample geometry. Okay, I'm going to switch gears a little bit. I'm going to talk about grazing incidence diffraction. Again, we're sort of talking about primarily polycrystalline samples or powders. And so this is fairly specific to beamline 11.3, although it is an issue at any of the other beamlines as well, but especially so at 11.3. And so this is, again, a picture. Your sample would sit here. The beam is coming this way and scatters into a large area detector. And what I want to talk about is, again, thinking of Q as a vector and what directions you're actually probing structure in. So if you're looking at a fixed incidence angle, and that's typically something very small, certainly below 5 degrees, maybe as low as 0.08 degrees incidence angle, you have an issue with the fact that if the incidence and exit angles are the same, then your Q vector is exactly out of the plane of your sample. And so that's satisfied for one single point on your detector. But if the incidence and exit angles are not the same, then Q actually starts to tilt out of the surface normal a little bit, and you have some small component that has some small in-plane component in your Q vector. And so what you start seeing is no longer the purely out of plane, but now some mix of out of plane and in-plane structure. And so what this means is that especially for things that are highly textured, such as this polymer system, this is not purely the scattering from the out-of-plane region, because you're not actually measuring the out-of-plane direction except for a point that's maybe here, single point on your detector. And so what you actually have is sort of a missing wedge. If you translate this into in-plane and out-of-plane, there's actually this section here that you cannot measure in a grazing incidence geometry. So I cannot measure the purely out-of-plane scattering at a Q of, say, 1.5 without going to a very high incidence angle. And so if you're interested in this, you may have to go back and do specular measurements on a different instrument, perhaps, to really fill in that missing wedge to get a full picture of your scattering space. So again, something that you need to consider carefully when designing your experiment, especially if you have films that are highly textured. So just a brief overview of then the considerations for a thin film geometry. If you have a thin film or something that is very weakly scattering, typically you should work at very grazing incidence to enhance the signal from the film and reduce the signal from the substrate. And this may be something near the critical angle, which is sort of around 0.1 degrees incidence angle. If you have a thicker film or something that scatters very strongly, it's probably better to work at moderate incidence angles of maybe a couple of degrees, because this gives you improved resolution because your footprint gets smaller, and so the projection of the footprint onto the detector gets smaller. You get better resolution, and you get reasonable signal to background ratio. You're going to be looking at less material that you care about, more substrate that you don't care about, but if the scattering from your film is strong, that's okay. You'd rather get the better resolution and suffer a little bit of signal. And so again, this is typically an incidence angle of a couple of degrees. And so again, think about what you're trying to learn and what kind of sample you have. And maybe you want to do this at multiple incidence angles, especially if you care about filling in that missing wedge. So this is very much sample dependent. Make sure you know what you want to learn before you come and do the experiment. Okay. There's a lot of techniques to cover, so we're going to jump around a little bit. I'm going to talk briefly about X-ray reflectivity. So this is a very surface-sensitive technique that lets you characterize thin films, multi-layers. Basically what you're learning is how thick each of your layers is in a layered system, and to some extent what the material is composed of. And so I'm not going to go through a lot of the theory, but I will say you're always working in this specular condition, so you're looking purely at the out-of-plane direction. So the incidence angle and the exit angle are the same. And then you basically can define a single angle, theta, and look at the intensity as a function of that angle. And so typically for a single smooth film, that's going to look like this black line here. So if you're at very low angle, you actually get total reflection. Then you'll hit the critical angle, at which point it starts to fall off. So the critical angle is the angle at which below you get total reflection. Above that, you don't get total reflection and the intensity starts to fall. If you have a very rough sample, this fall off happens much more quickly. If you have a film on top, you're going to end up with these oscillations. The frequency of that tells you about what the thickness of that layer is. And then sort of the amplitude of that oscillation tells you about the electron density contrast between the film and the substrate. And this gets much more complicated if you have multiple layers. All of these different things start to interfere, but we're going to consider a fairly simple case for right now. This is what data would actually look like. Below the critical angle, sometimes things are a little bit funny because your sample is not always as long as the footprint of the beam is. And so if the footprint of the beam would be bigger than your sample, you only reflect from the fraction of it that's actually on the sample. And so you can get sort of this strange shape that moves up as you change. This is a very simple experimental setup, typically. You have an incident beam, you have some slits to sort of define your beam, you have the sample, and then you have a point detector and some slits to basically collimate the scattering so that you can cut down on a little bit of background. So anything that scatters from here shouldn't be able to make it through the slits and into the detector. So it's a fairly simple setup. If you can look at the frequency of the oscillations, you can basically pull out the thickness. So the delta Q from minima to minima is going to look like 2 pi over the thickness of that film. And so this is a pretty easy way to get a very quick determination of a film thickness. You can do better if you actually fit the whole thing, of course, because you can get a more accurate determination of the thickness, and you can get an idea of what the depth resolved scattering length density looks like. This is roughly equivalent to electron density as well. So you can figure out more or less what your materials are. So if I have a light film on top of a heavy substrate, then my scattering intensity will drop, and then I go to air where it drops significantly, and you can see that maybe there's some roughness involved so that that transition is not completely abrupt. And so you can fit the roughness of an interface or a surface, the density, and then of course the thickness of this. And so it's really looking at out-of-plane structure. You can get very accurate thicknesses and good estimates of roughness. It can't actually discriminate between different types of roughness. So you can think about roughness either as an abrupt transition with a poorly defined position, so sort of a wavy line where you go from one material to the next, or you can think of something sort of as interdiffusion where that transition from one material to the other is not so abrupt, but they sort of blend from one to the other. You can't actually discriminate between those two in standard reflectivity measurements. You have to do something a little more complicated, and it's quite difficult. And the sample requirements for reflectivity are fairly high. You need something that is very smooth and very flat. And so a necessary but far from sufficient condition is if you look at your film and you cannot see a good reflection that looks like a mirror, it's almost certainly not going to work for reflectivity. Now, even if it's mirror-like, that doesn't mean that it will work for reflectivity, but it's at least a very good starting point. Okay, so sticking with surfaces but changing techniques, we're now going to look at much more atomic level structure of a surface or a film or an interface. And this is something called crystal truncation rod analysis. And so we'll skim through some of this. There's some of the basic diffraction theory to build this up, but you have an incident plane wave. It scatters off of something into a spherical wave. Basically what I want to get to is this. So Linson talked about what scattering from an atom looks like. He talked about what scattering from a unit cell or crystalline unit cell of atoms looks like. I want to consider what scattering looks like from a two-dimensional plane of regularly spaced atoms. So you can think of this as a crystal where I've cut out a slice that is only one unit cell thick, or better yet, one layer of atoms thick. And what does that look like? So we have essentially the scattering from, sort of all the prefactor. This is the scattering from the atom, this little f, in the unit cell. So we have the position and the q at which we scatter into. So we can sum over the atoms in the unit cell, and then we can basically sum over the unit cells along all the lattice directions. And if we want to consider just a two-dimensional plane, we throw one of these away because we don't have any repeating units in that direction. So we can get rid of one of them. And so we're left with basically these two repeating units. And then we can notice that these look like a geometric sum. And if they are a geometric sum, we can write down what they converge to. And so if we take one of these summations over a lattice direction, we rewrite it like this. It looks like a geometric sum, which means that we can rewrite it like this and get rid of that summation. So this is quite handy, because now what we can do is we can look at what the scattering from this plane looks like. We have all of this stuff that looks like a single unit cell, and then we have these two factors for all the repeats along one direction and along the other direction. And what this ends up looking like then is that the scattering from a two-dimensional plane gives you these rods in reciprocal space. And so if I'm looking in the out-of-plane direction, the scattering is nice and continuous along that direction. If I'm looking in plane, it's discrete. And so going from one of these halfway to the next one, I'm going to not see any intensity. But if I'm looking along the z direction, it's actually continuous scattering. Okay, so basically what this means is that something that is well-defined and isolated in real space leads to a very extended feature in reciprocal space, and vice versa. So we can then think about, okay, instead of a single plane of atoms, let's take a full three-dimensional repeating unit and just chop it in half. And so basically everything above a certain layer is gone, and everything below it is still a nice crystalline material. That means I need to add back in this third term, because now I am summing over unit cells in the third direction. I'm going to ignore these two terms for now, just for the sake of ease. And basically, because I'm going from basically nothing to a continuous number of unit cells, my scattering is going to look like the scattering from a single unit cell times this factor. And if you look at what that is, you get these big dips away from the Bragg peaks, and then you get these big things where you should have a Bragg peak. So this is now L in the HKL Miller indices. This is calculated for silicon, so I don't actually have all L's don't have a Bragg peak. As Linson was saying, depending on what the structure factor is, some of these may be 0. But I do have this overall shape, which is characteristic of a truncated crystal. I can build up then a more complicated thing by saying, skip that one and go to here. If these black circles are my truncated crystal, then I know what the scattering from that looks like. And then if I want to put layers of atoms on top, I know what the scattering from those layers of atoms look like as well. And so then I know what this total scattering from this system looks like, which is just the scattering from the surface layers plus the scattering from the bulk, the truncated bulk. And so I can actually figure out what the scattering, not simply at the Bragg points, will look like, but between the Bragg points as well for this sort of system. And what you find if you do some modeling, this is actually very, very sensitive. So what I have here is simply a piece of silicon. And if you look at the blue, this is for a 00L, and this is for a 20L. You see this characteristic shape. If I stick something in that surface, and this is something very light, this is just some lithium, so it's not a very strong scatterer, you end up with this red curve. And so you see that you get a significant change in the shape in the 00L, and you also get sort of an up and down behavior in these troughs for the 20L. It becomes even more dramatic if I take the top layer of silicon atoms and just move them slightly up. So I let them relax out a little bit, and then you get this green curve, which you can see is significantly different from the unrelaxed surface. And so you're very sensitive in this kind of measurement to very, very subtle structural distortions at a surface or at an interface. To measure one of these, you do need a lot of degrees of freedom, typically a 4 circle or a 6 circle. And what we're doing now is using small area detectors to measure those peaks, so you don't have to scan across a peak. And so this is a schematic of what 7.2 looks like. Your sample would sit here, the beam would come here. I can rotate the sample this way, I can rotate it in here, I can rotate that whole thing this way, and then I can rotate the entire thing using this circle down here, and then my detector I can move up and down or side to side as well. So I can really look anywhere I want in a reciprocal space using one of these instruments, which is important. Let's see. What that looks like, we didn't really go into what the Ewald sphere is and what this looks like, but in reciprocal space, this is essentially what my small area detector would see. And then this is my crystal truncation rod from a surface. And as I move the orientation of my crystal and I move my detector, I'm going to move along this rod. And what I'm going to measure is where this Ewald sphere intersects this Bragg rod, and that's going to show up as the intensity on my detector. And so what you'll see then is that you'll get these oscillations of strong intensity and weak intensity as you move along this rod. And so there it's getting weaker. You're going to come up close to a Bragg point. It also shows you L here, so as L gets close to an integer value, this will get stronger. So as it approaches 4, it starts to get strong again. When it's at half integer values, it's at its weakest. So when you're away from the Bragg points, it's very weak. When you're close to the Bragg points, it's very strong. And so what you can see then are things like out-of-plane spacing changes. And so if the surface relaxes and either contracts a little bit or expands a little bit, you can see if the in-plane spacing changes at the surface or if the periodicity at the surface changes. So if I lose every other atom on my surface layer, that's something that I can easily see. That's typically called a reconstruction. I'm not going to go over that too much because we're getting a little bit short on time. But there are different ways of talking about these. So basically, my periodicity of my surface layer can change, and it can change quite dramatically. So instead of this little square being my unit cell at the surface, the periodicity might change such that it's now a 6 by 2. Or it may rotate. So in this case, it's a square root of 5 square. So the edges of this are the square root of 5 times the original. And then the whole thing is rotated by 26.6 degrees. And so that this becomes my new repeating unit on the surface. And that's typically just referred to in this nomenclature. And what this will give you then is if you have a reconstruction at the surface that gives you a larger periodicity, it gives you extra points in reciprocal space. So basically you're going to get superlattice peaks corresponding to half integer values or fractional integer values of where the bulk Bragg peaks would be. So if this is the 110 peak, this would be the half 10 peak, which in the bulk, there shouldn't be any intensity there, but because my surface may have reconstructed, I might now see a feature at that point. And so some considerations then for thin film diffraction and CTR specifically, it's very sensitive for looking at epitaxial thin films or surface structure of crystals. You need really high quality samples on a crystalline substrate because the entire system needs to be essentially single crystal. And also alignment is very demanding, and it's very important to keep that in mind, and don't take shortcuts at the stage of alignment. If your sample is not very, very well aligned, you're going to have a very, very hard time going and finding the feature that you want in reciprocal space because you're just going to be looking slightly off of where it should be. And so make sure that you don't skip out on that stage. But it is very sensitive. It is so sensitive that you should be very careful about the conditions that you do the measurement in. It's not unheard of that simply by putting the X-rays on your sample, you've changed the surface, especially if it is in the presence of water or oxygen. And so you want to think carefully about that and make sure that by doing the measurement, you're not changing the thing that you want to measure. And always make sure you go and look for those fractional rods because there may be a surface reconstruction. You want to make sure that you don't miss it. Okay. We have about 15 minutes before the break, so I'm going to briefly do an overview of some other techniques that you might consider. and then wrap it up with hopefully a few minutes for some questions and discussion. So I've been talking a lot about scattering. Scattering tells you basically things like the unit cell size, strain, crystallite orientation. You can use it for identifying what phases you have. Basically, you're answering questions of where are the atoms. The other technique that we're not covering in this school is spectroscopy, which tells you things like what is the local environment and what is the oxidation state of an atom, and it's much more element specific. So it turns out you can combine these. Most of our beamlines, all but 11.3, let you change the X-ray energy, and so you can actually tune to a resonant absorption edge for a certain element. And so the example I'm going to give for this is a material that contains copper, zinc, tin, and selenium. And it turns out that scattering, as Linson was saying, goes as the atomic number. And so the scattering difference between copper and zinc, they only differ by 1 electron. It's very, very small. So it's very difficult to tell zinc from copper in a diffraction experiment. But if I tune my X-ray energy to just around the absorption edge of one of those elements, I can actually change the scattering power of that atom in a somewhat understandable and known way. And so this is what a classical absorption spectrum would look like. If you do the Kramers-Kronig transform of that, you end up with this, which is basically the change in the scattering power. And so if I'm very, very far away from resonance, it's basically 0. But if I'm right at that absorption edge, I can actually make it change by as many as maybe 10 electrons. And so I can make an atom look like something 10 electrons lighter than what it actually is. And so I can get good contrast between something like copper and zinc if I'm near one of their absorption edges. And so this is an example. In this material, there was some debate as to how the copper and zinc get organized in this structure. And so this is the nominal answer. So these are my zinc atoms, these are my copper atoms. And you can see one of the other alternatives is that in that layer it's all copper, and then this one, instead of being copper, would be zinc. And these two are almost identical in the diffraction. You would need amazingly good diffraction data to even think that you could tell these apart if you're not working near resonance. But if you tune the X-ray energy that you're using, and you pick a certain peak, so this is the 002 Bragg peak, you see that they would have very different behaviors depending on the ordering of the copper and the zinc. And so if it's this one on the right, I would end up with this black curve as I change the energy. If it's the one on the left, I would end up with this blue curve. And if it's sort of a random distribution of the two, I'd end up with this red curve. And so you can measure the powder diffraction, and you can look at some of the peaks that might be especially sensitive to this, in which case there are these first 3. And I can measure those 3 peaks as a function of energy. And you can see this is where now color is basically corresponding to intensity, and so I can see that it's brighter here, weaker here, a bit brighter here. And if I plot that more as a function of intensity versus energy, you see that you get this these very characteristic shapes. There is one thing, this drop here is basically as I move across the absorption edge, I change the absorption of my sample. So I have to account for that, but you can model it. And so if you actually model, you can actually fit these curves, that you can fit the peak intensities as a function of energy, and you can refine the occupancy of the copper and the zinc on the different sites. And this is something that you wouldn't be able to do if you couldn't tune the energy. So that means that this is something completely impossible on a lab source. You really need a synchrotron to do it, and you need a tunable beamline. This is just the absorption correction. This resonant trick works for more than just powder diffraction. You can do it in reflectivity. So if I work very near an absorption edge, I can start to get enhanced sensitivity to something like maybe a native oxide layer, or something with very similar electron density but different atomic composition. And so you can basically enhance your contrast by tuning your energy to a resonant edge. Okay, this will be the last thing I talk about, and then we'll end and have some time for questions. The other thing that you may want to do is depth profile your sample. So especially in a thin film, the surface may be different from the bulk of the film. And you want to be able to isolate just the surface from more of the bulk film. And you can do this if you can tune the incidence angle very carefully. So we talked about the critical angle very briefly. And if you're working, so this is a reflectivity curve for some complicated layered system. If you're working below the critical angle, you can actually calculate the penetration depth, and until you hit that critical angle, it's pretty much flat, and it's really only maybe a nanometer or less penetration into the sample. And so you can really isolate below the critical angle the top, say, nanometer of material from your sample. And as soon as you go a little bit deeper, you see that now suddenly you're probing on the order of 100 or more nanometers of the film. And so you can really start to separate out surface from bulk effects in a thin film type of material. It's tricky. It again requires a very smooth and flat sample, but it can be done. And in this case, I was looking at sort of an amorphous oxide on top of a film. And so if I'm looking right here well below the critical angle, so I'm looking at just the most surface, I see that there's really no sharp features in the scattering. And if I go just a little bit higher in angle, suddenly all of the Bragg peaks start showing up as I start to become more sensitive to the bulk. And so this is another trick that you can play, and something to think very carefully about what the correct geometry and design of an experiment is. Doug will talk a little bit about some operando work. So just a quick review, the 5 main scattering beamlines that we have at SSRL. You can do a lot of different techniques. Borong will talk a little bit about this later, but something that's unique to SSRL, our beam time proposals are not beamline specific. So if you need to combine some of these techniques to get a full picture of what your material is doing, you can do that, and you can do it on a single proposal. Most of the beamlines are fairly easy to reconfigure according to your needs, and we're definitely happy to work with you on making sure you have the best setup for your experiments. So please, talk to us. We're happy to help and happy to discuss. Some quick acknowledgments for people whose data I've shown. Mike Toney and all of the members of his group, Chris Tassoni and his group, and Laura Schellis, all were involved in some of the data that I've shown, so I want to thank them. And just leave you with this. Basically, find the measurement approach and the geometry that works best for your sample. And it's not necessarily the thing that makes the measurement easier, it's the thing that gives you the best data for what you want to know. And so really think carefully about what that is that you want to know, and what data you need to tell you that. And thank you. So I'm happy to take any questions or discussions before the break, if there are any. Yeah. Oh, sorry. Can you use the microphone so we get it captured?
When you do resonant diffraction, how do you identify which peaks are going to be the most valuable ones to look at?
You have to do simulations. So not all Bragg peaks will behave the same way in response to tuning the energy. And some of them, in this case, in the case of CZTS, which is what I was looking at here, basically, these 3 peaks were sensitive, and if you calculate what this big one does, which is sort of the one you'd want to look at because it's your strongest peak, it turns out it behaves the same way no matter how you organize the copper and zinc. So you really have to just simulate what the response is and figure out what peak is going to give you the most sensitivity to what you want to know.
Okay, thanks.
Yeah, Lindsay?
So what do you do about footprint correction other than moving to a point detector?
Ideally, you minimize it. So you either make your beam short, as short as you can, so that the footprint is small, or you work at a higher angle. But if you can't do either of those things, and there are definitely times when you can't, you can try to characterize the instrument response. So if you measure something, so the measured peak shape is going to be a convolution of the inherent instrument response, which is basically that footprint, and then whatever the inherent peak shape from your sample would be. So if you have things that give you a broader peak that are in the sample, what you measure is a convolution of that and what the instrument response would be for something that's a perfect sample. And so you can try to deconvolve those. For something like the footprint correction, it's difficult because it's basically a top hat shape. So really what you try to do is minimize it by playing with the geometry of the measurement as much as you can. Okay. Any other questions? Okay, well, I'm here, so come talk to me if anything comes up, and happy to discuss. But if not, then we'll take a break, and I don't have the schedule in front of me, but reconvene in something like 20 minutes for the next set of talks. Thanks.